baby shawties? How we doing? Big things today. So what we're going to talk about today is what's called Coulombs Law. So Coulombs Law is going to describe the force of attraction or repulsion that goes on between two charges. And what Coulombs Law is going to do is it's going to get mathy with it, and it's going to give us a magnitude to the amount of force that's actually going on in between two charges. What we've talked about at this point already is the basic law of electrostatics that says if we have two like charges, whether positive or whether negative, that they would always repel each other. And if we have two opposite charges, they're always going to attract each other. So what this law is going to do is it's going to get quantitative with it, where we're actually going to fit numbers to these things. So it's going to depend on really two things. So the force of attraction or repulsion, known as the electrostatic force, is going to be directly related to the two charges. Okay, so directly related, you'll see on top here, we're going to multiply the two charges together. Our charge is going to be labeled as Q1, whoopsie daisies, it's going to be labeled as Q1 and Q2. So we're not using the letter C to represent charge, we're using the letter Q. That comes from the idea of charge being quantized. Quantized means that charge is basically little bundles of electrons, so we use the letter Q to represent that. So we have Q1 and Q2, which is going to represent the magnitude of the two charges, and it's going to be inversely related to the distance between those two things squared. So the distance is going to be the separation between those two objects, and we're going to go through some examples, but the force is going to be, again, directly related to the charge. So the more charge that we have, the greater that force should be. It's going to be inversely related to the distance squared. So if I look at the distance here in the denominator, what that means is that the greater the distance, the weaker that force is going to be. So Coulomb's law is going to relate the force of attraction and repulsion between these two things. Last thing to note here is that this does find the magnitude of the forces. So always remember the basic law of electrostatics, that if we have like charges, they will repel, opposite charges, they will attract. This equation doesn't really need to be used to figure out whether it's attraction or repulsion. That's something we should already know. So more in terms of the variables, so F obviously is representing the force, which we're going to measure in newtons. We talked about Q1 and Q2 represent the charges on each object, again, and we're looking at the magnitude of the charge. Remember, when we talk about the magnitude of the charge, we're talking about this in terms of coulombs, okay? Along with this, because we are dealing again with charge being the number of electrons or excess electrons something has or lack of, know that we might see these as smaller numbers. So you might see things like 10 to the negative 6 or 10 to the negative 9th. Just know that those are representing very small numbers because charge is very small because it's dealing with the number of electrons. And then we're looking at the distance between the two objects, which again, distance always measured in meters. There is one thing within this equation. There is this value of K. So K represents what's called Coulomb's constant. So Coulomb's constant is always going to be this value of 9 times 10 to the 9th. And the units would be Newton meters squared over Coulomb squared. We don't have to worry too much about the units. But it's called a constant because this value is always going to be there. It's just a part of this equation. Okay, this equation obviously was derived through experimentation. So K was a constant of proportionality that was always found to be present within this. So we just call this Coulomb's constant. That's always going to be included in the equation. Okay, these first two examples, what we're going to do is just talk about how we actually use Coulomb's law. So again, Coulomb's law, just right on top here, is going to be that K, Q1, Q2 over distance squared. So K is that Coulomb's constant of 9 times 10 to the 9th. Q1 and Q2 represent the charge of each object, and D represents the distance between them. So in this problem, we were given a amount of charge of 1 coulomb. Okay, so on our perspective, 1 coulomb, coulombs is our unit of charge, so the value of 1 would be a single coulomb of charge. And then the distance here is 1 meter, which think of it the length of a meter stick. That would be the distance between those two charge objects. Our goal is to figure out the force between them. Okay, so to find the force, I'm just going to use that equation up top, and I'm going to plug in my values. So the values I would plug in are that K value of 9 times 10 to the 9th. I'd plug in each of my values for coulombs or charge. So I'd have 1 coulomb for Q1, 1 coulomb for Q2, and then the distance between them is also be 1 meter squared. Okay, plug in the units there just so we can kind of see what's going on. All right, so real quick, punching in our calculator, we want to be careful, making sure we're using parentheses around things, make sure we're distinguishing between the numerator, which is on top, and how we're plugging that in possibly first, and separating that out from the denominator. And don't forget about that square distance on the bottom. But when you plug that in, what you should get is about 9 times 10 to the 9th newtons, which is the same thing as saying 9 billion newtons of force. Okay, so what I want to show here is that when we talk about the force of attraction or repulsion between two charges, in this case, obviously since they're the same charge, we'd be dealing with repulsion, that if we see things like a single coulomb at this distance, they produce really, really big forces. So to put in perspective, my weight in newtons is about 1,000 newtons. Okay, so you're talking about 9 billion newtons as the force between two charges that have 1 coulomb of charge. Now, the reason why this value is so big is because it's hard for us to recognize, but 1 coulomb of charge is actually a very, 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 very large amount of charge. So we're going to see, like I said before, you're going to see some numbers that are a little bit more relatable to what's actually going on. Electrons are very, very small. So this would mean that that object has accumulated a bunch of electrons, or in this case, since it's being positive, lost a bunch of electrons. So what that means in terms of the problems you're going to see is you're going to see charges at a smaller level that's going to relate a little bit more towards the electrons. Now what that's going to do then is it's going to bring, if we're to look at the charge of objects related to electrons, you're going to see things of smaller charge. So even though 1 coulomb, the number 1, is a small number for us, again, and the size of the electron, that's actually pretty large. And notice again the force that it creates. So in example 2, we're going to get just a little bit more relative to the size of an electron. So in this problem, you're going to see the charge that we're given here. We have 2 identical balloons, both having negative 6.25 NC. So know that's that negative 6.25 NC. Key thing here, NC, the prefix N, stuff we talked about at the beginning of the year, this represents what's called nano. So N represents nano, and nano means 10 to the negative 9th. Okay, so that's an order of 10 down to the negative 9th, so that's like the billionth in terms of our decimal. So that really means that this charge is negative 6.25 times 10 to the negative 9th coulombs. But again, this number is going to make a little bit more sense because the size of an electron is very small. So what we're going to do is we're going to calculate that same force of, in this case, of repulsion again, because we're dealing with 2 negatively charged balloons. But now we're going to use numbers that might be a little bit more relatable to the scale of electrons. But again, our equation is still going to be the same. We're still going to use that K value, that Coulomb's constant of 9 times 10 to the 9th. We're going to multiply it by our 2 charges, which would be negative 6.25 times 10 to the negative 9th. Just to kind of shorten this a little bit, since both of my charges are the same, like here I had 1 and 1, if both charges are the same, I can shorten this down to say maybe squared. I'm going to square that charge because I'm going to multiply by the same number twice. And let's say that I'm going to divide it by the distance, and here the distance is 0.06, and then that's going to be squared. So again, that's going to give us our overall force of repulsion between these 2 balloons. Okay, so we're going to use a small number here, so the force we're going to get is about 0.0400000 and about 98, we'll round it there, that'd be newtons. So again, it's a very small force. Since it's very small, we can write this in scientific notation, so about 9.8, and if I were to move that decimal over to the right, I'd have to move it 5 spots, so we could say 9.8 times 10 to the negative 5th. I'm going to use a negative exponent because it's a small number. So that'd be the force if we had a charge of negative 6.25 nanocoulombs. So notice when we bring the charge down relative to the scale of an electron, that's going to lower the force to something we're going to see. Now think about the forces we were seeing in class with some of the experiments we were doing. The sense of attraction or repulsion was not that great. Okay, it was sometimes very subtle. It wasn't something like 9 billion newtons that we were seeing. So on the scale of electrons, it's going to be smaller forces. All right, next examples, again, we're going to look at same idea, but now we're going to do something a little bit different. We're going to look at different charges. So here I have 2 charges, one of which is positive 3.37 MC. MC means millicoulombs. And then we have negative 8.21 millicoulombs, and they are held at a larger distance of 2 meters apart. So because they're opposite charges, first of all, we know that this is going to be a force of attraction. Again, so I'm going to use my Coulombs Law equation, plugging in that K value and my two charges and the distance. The only difference here is that when we see MC, that's going to mean millicoulombs. Milli is a prefix of 10 to the negative third. So I'd have 3.37 times 10 to the negative third and negative 8.21 times 10 to the negative third. So plugging that into my equation, should look something like this. Again, my K value, my two charges. I didn't put the positive and the negative here just again because I know from them being positive and negative, I'm going to get a force of attraction. So the sign doesn't really matter. This force again is going to just be, or this equation is going to give us the magnitude. And then I have my distance squared. So plugging that all in, I will get a force of attraction of 62,252 newtons. So again, a bigger number. So that is because we're dealing with millicoulombs. So we looked at nanocoulombs, millicoulombs. So to kind of get a number that's going to be more relative to our scale. Along the same lines, just as a heads up, you might see that prefix mu, which again represents microcoulombs, which would mean that we have 10 to the negative 6 coulombs. So you might see nano, might see milli, might see micro. And again, those prefixes are going to put things kind of in the scale of an electron at our level. All right, last one here, we have a balloon with a charge of 4 millicoulombs is held at a distance of 0.70 meters. From a second balloon having the same charge, what is the electrical force between them? So why don't you guys try this one on your own? So pause the video using this Coulombs Law equation, see if you can figure out that force between those two charges. So your force you should get is 293,878 newtons. I kind of did a shortcut method here again since they were both the same charge. I just took the charge of that, 10 to the negative third is for milli, and I just squared that to represent both the charges of each balloon. So again, this is using the Coulombs Law equation to figure out the force of attraction or repulsion between two charged objects. Next example we're going to do is we're going to use that Newton's Law equation again, but now we're going to look at how do the variables affect the overall force that we're seeing. So just to quickly do this one, we're just going to set this up. I have, let's say, a 2 coulomb charge is held 10 centimeters away from a negative 3 coulomb charge. What is the force of attraction between them? So again, we're going to get probably a larger number here just because we're using larger charges. And if to plug that in, we should get 5.4 times 10 to the 12th newtons. So 10 to the 12th, again, that's going to be a very large amount of force. And as I talked about, 2 coulombs and 3 coulombs is a pretty large amount of charge that an object would have. But nevertheless, what we're going to do is we're going to look at then how would this value of 5.4 times 10 to the 12th, how would this change if I were to make changes to my original values in my equation? So in A, we're going to look at what would happen if I were to double the 2 coulomb charge. So that means if I were to take this 2 coulomb charge and double it to make it 4, how would it affect that number? Okay, so what we're going to do is we're going to plug this same thing into our calculators, and we're just going to change that 2 to a 4. Okay, and what you should get is about 1.08 times 10 to the 13th. I rewrote this for you guys. Same thing as saying 10.8 times 10 to the 12th. So how does that compare to 5.4? So thinking 10.8 compared to 5.4, what we should see is that this also is doubled. So when we doubled one of the charges, we're going to see that the force is also doubled. And that should make sense. If we have a larger amount of charge, the force should also get bigger. B wants to know how will the force change if the distance between them is doubled. So what I'm going to do in this one is I'm going to change now the distance from 0.10, and I'm going to double that. So that would be then 0.20 meters for my distance. And what would that create for my force? While I do this, I'm again to make sure that I keep everything else constant. What I get then is 1.35 times 10 to the 12th. So you'll notice just based on values, order of 10 stayed the same, but we see that now this value went from 5.4 down to 1.35. So we see that it decreased, but I want to know by what factor did it decrease. So real quick, just to do the math here, if I took the original value 5.4 and it went down to 1.35, let me just divide those two numbers, and what I would get is 4. Okay, so what happens is that this decreased by a factor of 4, which means it was also cut into fourth. Okay, and this is what's called the inverse square law. So when I doubled the distance, it didn't just cut the force in half, but it cut it into into fourth. So it's technically 4 times smaller than what it does. That's what's known as an inverse square law. So let's kind of see if we can think about the same thing, but now instead of doubling the distance, I'm going to cut the distance in half, meaning I'm going to bring those two charged objects closer to each other. So if I were to take 0.10 and cut it in half, my distance is now going to be 0.05 meters. So if I do that, I would get a force equal to 2.16 times 10 to the 13th newtons, which is the same thing as saying 21.6 times 10 to the 12th. So again, comparing values, that 5.4 turned into 21.6. So if I wanted to compare those, again, I'll just do what I did before. I'll take the 21.6, which is the larger, divide it by 5.4, and what you should get is 4. The only difference is that the force got bigger, so here it's 4 times larger when we cut that distance in half. So this is what's known as the inverse square law, that as the distance gets bigger, the force is going to decrease at a square value. Okay, same thing if we cut the distance in half or into smaller chunks, the force is actually going to increase, but at a square value. All right, so if we were to graph this, you would see some sort of parabola, whether it's decreasing at that rate or increasing at a square rate to form that sort of parabola. All right, so these examples, I know the numbers were a little bit different for us, so don't get confused by the numbers, but it's just this Coulombs Law equation is allowing us to solve for the magnitude, which is the value of the force between any two charged objects. And again, this force is going to range, on our level, could be a very big force, so we're going to see some different things in terms of the numbers to kind of fit these problems. All right, so we're going to finish. We have another video lesson in the following examples, but we're going to go through how to apply this to different situations since we're now talking about forces. How do we apply this to balanced and unbalanced forces, things we talked about throughout the year. If you have any questions on this stuff, make sure you jot it down. We'll get some practice with Coulombs Law. We'll see you guys later. Peace out.